All right, so I had an idea for how to improve MIRA, basically, and it turns out it's fairly similar to their idea, and I think this screencast may help provide motivation for their full idea. In this screencast, we're just going to work with the binary case of two classes, and basically we're going to look at MIRA as a rotation, and then we're going to say, oh, we could over-rotate so that we get the best margin, and I'll go over a way to implement this, and we'll be able to implement a small angle approximation of this idea, which will be simpler. And then if we don't know gamma, the separation, then we'll talk about some ways that we can figure it out. And then we're going to take this and we'll see how MIRA basically comes out of this. Basically, if we don't know gamma, we can let it adapt dynamically. And that's how we're going to get MIRA, from a small approximation, angle approximation with adaptive gamma changing. And then I just have a few extra ideas I want to share. So let's get started. So first of all, let's say that we have our initial vector like this, and then we pick this point. And this is a blue point, but our vector would classify this as the dot product would be negative, and so it would classify it as purple. So we need to update. And if you remember, we just subtract off the projection of this onto this vector, and so then we get this as our new point. And so now all points on this side will be classified as blue, all points on that side will be classified as purple, and we can see that this point here is just on the borderline, right? So there's zero margin. All right. Okay, so it would be nice to have a bit more margin. And we can think of this as we just rotated this vector by a certain angle, theta. Since only the direction really matters, right? So yeah, we made it a little bit shorter in MIRA, but whether it's longer or shorter doesn't matter, only its direction matters for how it's going to classify things. And we just rotated it so that this was absolutely perpendicular to that. So maybe if we rotate this a little bit more, then we'll get a better, error bound. So that's basically the idea. And so next we're going to talk about how much we can over-rotate here. And so I'm going to try and shrink this here. Hopefully this works. Yay. Okay. I'll just bring this up. Okay. So how much should we over-rotate to get the best margin? Well, we know that this distance can be up to r, right? Less than or equal to r. And we are assuming a separation of gamma, right? And so that this distance is less than gamma. No, greater than or equal to gamma. Which, I'm just going to do a simple approximation here. This arc length also will be greater than gamma, right? And they should be about the same if our vector is fairly good. So that means that this, ideally we would want to say this was our vector, right? And we pick this point. Well, we want to, let me go back a step. Say this is our vector. Well, we'd want to rotate it to perpendicular first, and then we want to rotate it an extra amount. If I rotate it to perpendicular, this one's halfway in between being classified as each class. But I want to rotate it by another amount of this angle, right? to get a vector that's basically pointing up. That angle will be the same as that. And we know that this angle, theta, is going to be less than or equal to gamma over r, just using a small angle approximation in radians, since this is bigger than r and this length is less than gamma. All right, and so to be conservative, let's choose this theta to be gamma over r. So how much can we over-rotate? A little bit more than gamma divided by r. To be conservative, we'll just rotate by the angle gamma. Now let's implement this. So first of all, what I'm doing is this is just the MIRA update to make it perpendicular. And then I'm normalizing it so it has length 1, so that v is a unit vector. And now I'm basically going to rotate it slightly. So let's call this point here p hat, the actual point that we're using for our update. So I noticed here we have two classes, and the vector is supposed to be pointing towards the blue class. So I guess what I need in here is I need y. So y equals 1 if blue, and -1 if purple. So if it's blue, we're going to end up going, v is in the opposite direction. Yeah. Whereas if it's purple, they're in the same direction, but we don't want to go in that direction. Hold on a sec. Yep, this is actually fine. I don't actually need y in there. Now let's consider this one. So we normalize it, and then p hat times gamma over r. So that would rotate it towards the point. And so here, this is where I need this is a gamma. And then I'm also going to need my y, which will be plus or minus 1. Because if it's not the class that I'm supposed to be pointing to, I want to rotate away. Okay. And so this is basically, we've got v vector. Presumably, v vector is now perpendicular to our p hat. And presumably this is some fairly small number, because r would be much bigger than gamma. And so we're just going to add, this is length 1, this will be length gamma over r, which means that this angle, theta, will be approximately gamma over r. Okay, so this is just an implementation using vectors, which is approximately correct. Yeah. Now, what can happen here is so I'm going to shrink this. So that was our picture. We rotate it. Now this should give us something pretty close to the optimal angle, but we're only going to keep this if v dot p vector increased, right? Sorry, v dot p times y increased. So if y is negative, then we do want a negative dot product. So more in the correct direction. So this is my alternative to only update if you make a mistake. Because say we pick this point and we have this green vector, well then our margin isn't big enough, so we're still going to want to rotate it a bit, right? But if we picked this point, say if we picked this point, then by making it perpendicular, first of all we would rotate it the other way, and then we'd rotate it back, and then maybe our vector, I want to pick an even more extreme example. Say we pick this point, so first of all we rotate to be perpendicular using the MIRA step, and then we make it, normalize it, and then we rotate it a little bit theta. Well, we've made our vector worse. It was pointing more in that direction initially. And so we really only want to update it in the cases that are close to being marginal, right? And right now the way I'm dealing with that is saying only keep the update if this dot product increased, so that we're more in the correct direction. All right, so now let's do a small angle approximation. I'm going to start again with a clean one of these. Let's shrink this. And bring this one up. Small angle approximation. After a little while, we can assume, I think, that most of the time V is close to perpendicular to P when an update is needed. Right? So our vector is pointing in close to the right direction. It might be a little bit off, but it's fairly close. So if this is true, in many directions it might take a little while. In very high dimensions, it might take a little while to get close to this. But if this is true, then so I don't think we really need to normalize in between. So we can make it perpendicular. Yeah, so I'm just going to change these steps a little bit. So we're going to scratch out that step, and then we just want to multiply. Just want to multiply by the length of V there. Yeah. So I've gotten rid of one step, and now I'm not normalizing V. I'm just multiplying by the length of V, so V could keep getting bigger or smaller. And now I'm going to, and we can scratch out this. And now I'm taking V, I'm subtracting this, then I'm adding this. I guess at this step we'd still want to only do that. Or better yet, let's combine these into one step. So actually I'll delete that. So V is going to be updated to V minus V dot P hat minus gamma over R times the length of V, all times P hat. Okay, so I've pretty much updated these. I've combined these two into one update. Since v dot p hat should be pretty small since they're mostly perpendicular. So this update should be very small, so that shouldn't change the size of v much. And so combining these, we'll get approximately this update. And there we have it. We're pretty close to their, we're pretty close to MIRA here. So basically, we're saying it's basically like we changed the dot product. So we made v vector dot p hat smaller by basically that angle. So it updates more aggressively. And a great thing about this is we only want to update it if v ends up more in the p hat direction, which means that overall, this term, this should be negative, right? And so this, I'll put this in quotes, because this is like our new substitute for the dot product. So if this new substitute dot product is negative, then we're actually going to make our update. So let's call this b tilde, because they use b for the dot product. This was just b in the paper, and so we'll call b tilde the entire thing. B tilde. So update only if b tilde is less than 0, right? Otherwise, don't update. So this is getting much nicer. Cool. So we're done our small angle approximation now. So far, I haven't used this. So I'll just copy another one down there. So here we assumed that we knew the separation and we knew the max norm R, so we could figure those out. So what if we don't know gamma? Since we've got a gamma in our formula, well, we could play around with different gammas. We can, so that would be the first thing, play around with different gammas. And we can go over a relatively small, not a really small, so a smaller number of data points repeatedly, initially, while we're trying to roughly estimate gamma. And so what's going to happen is if we make gamma too big, we might start here, and then after our rotation, we over-rotate, and now our new vector is here, and then we're going to misclassify a point over here, and then we're going to rotate to perpendicular, and then we over-rotate, and then we're back here, and then next time around we're going to misclassify this one again, so we're going to over-rotate. So we're going to keep misclassifying the same points, right? So if we go over, not too small, but we can go over a smaller number of data points repeatedly as we're trying to estimate our gamma, and that's going to, and that'll help us identify if we keep doing updates over and over and over again, then we're probably over-rotating, so our gamma is too big. So if we keep updating the same points, probably gamma is too big. It's probably possible to prove this. I think it's probably not worth the time though. And if gamma is small, is gamma, if the estimated gamma is less than 2 times the actual gamma, then it will converge, although the margin will be as large as, be back in a second. Right. Okay, so actually this is incorrect. If gamma is less than 2y, then it will correctly classify the points, right? If the estimated gamma is less than the actual gamma, then it will converge and correctly classify the points. So if we're, whoops, that should be a single gamma. So if it's bigger than a single gamma, then it's going to over-rotate a bit, and so it'll over-rotate back. Not so much that you're misclassifying points, but you'll just keep updating forever, which would be a pain. And so it'd be nice to have it be less than gamma. So the margin would be as, I should say, although the margin would be as small as gamma estimated. So if our estimated gamma is less than gamma, then in the end our margin will be less than gamma. Yeah, so we could just play around with different gammas to try and figure out a good one and then stick with that. So that would be one strategy. Or, right, strategies. Try to figure out about the right gamma. Or we could let the algorithm adaptively modify gamma. All right, and so this is what MIRA is going to do. It lets the algorithm adaptively modify gamma. So I'm thinking I might want another one of these. All right. Yeah, so MIRA lets the algorithm naturally adapt. So let's go back to here. So what we might want to do is initially start with a large value of gamma and then make gamma get smaller. And the way that we can do that is we're just gonna get rid of this. So what we're going to do is initially we want to have basically a really big gamma. And then over time we want to make gamma smaller and smaller. And so we're just going to get rid of that. And so initially, when v equals 0, it's like we just do a regular perceptron update. Right? Because the size doesn't actually matter, and so in terms of direction, we're in the direction of the first point. Then as v gets larger, since we erase the size of v here, basically this angle is getting smaller. So I guess the effective gamma is equal to the gamma I have here. I want some, I'm going to call this beta, which I think might be similar to the notation they use. So the effective gamma is going to be equal to beta divided by the modulus of v. Yeah. Cool. So as v gets bigger, the angle gets smaller. And as the angle gets smaller, we go more just back to regular MIRA. And we know regular MIRA, if we got rid of that term, well, this term is just always trying to make this vector as small as possible, right? And so we're going to get to a balance between trying to make the vector bigger and smaller. So one thing here, I said we do a regular perceptron update, regardless of whether the point was classified correctly. Yeah. Yeah. So that's going to make this grow. Yeah. So I can. It seems to me that this would work fairly well. I've been trying to analyze it, but it seems to me it's hard to analyze whether this will be totally optimal. But obviously, if our effective gamma is too small, then we're going to do mostly MIRA type updates, which will tend to make v smaller. And if our effective gamma is too big, then we're going to do primarily this kind of update, which will grow v, making the effective gamma smaller. So it seems like it should do roughly the right thing, and it adapts by itself, which is kind of cool. So we don't have to search over a parameter space like we would in this case. Yeah. So one assumption that I'm not sure if it's valid is we've been assuming that, here we've got a certain margin. This would be more than 2 gamma. And here we just assume it's more than 2 gamma 2. I'm not sure, but I think in some cases, maybe the separation here would tend to be bigger than the separation here. In which case, we could definitely modify these algorithms to take that into account, particularly when we think of rotating by an angle. If we think of rotating by an angle, then we just need separation by an angle. So we could have a bunch of points here, and then a bunch of other points down here, and then a certain, and then we can make this 2 theta. So we've got 2 theta separation. So we could modify our algorithms above to work for this case as well. Yeah, so that's a different kind of separation in angle instead of in terms of distance. And I'm curious in actual applications, which of these is more likely to occur. I mean, it could be something different than both of these cases as well. So anyways, there you go. Basically, we can think of MIRA as rotating until we're perpendicular, and we can over-rotate to get a good margin to figure out how much we should over-rotate by. We can basically play with different estimates of the separation and see whether we just keep updating because our estimate is too big. So basically we want the biggest gamma possible without making it too big so that we constantly make the same mistake over and over. And so we can search over the parameter space to try and figure out what gamma is, or we can let the algorithm adaptively modify gamma. And that's basically what MIRA does by striking out the V, and this parameter beta divided by V becomes our effective gamma, which will I think it should tend to be about the right value, but not necessarily exactly the right value. Yeah, thanks for watching.